What we're going to look at here today is a powerfile. So this has phase control in it for controlling the speed. Now I've got the CT connected to where the power goes through to the power plug, and I've got the probes on the mains voltage side. So as per convention, we've got the mains voltage displayed on channel A and the current on channel B. So I've got it set to 1, like so, and I'm going to hit the trigger. The trigger is just an on-off switch. The speed control's over here, so it's going to get loud. I'm afraid these things are noisy. So there we can see the conduction happens there, and then you see the current go down. Okay, once again there, it's still fairly small voltage, because with phase control what you're doing is phasing from that point backwards until you get to full conduction, which I'll show you in a moment. So this is minimum speed for this file. So it starts conducting at that point of the cycle, and that area over there is where voltage flows to the motor and current flows through the motor. So this is where you got current flow. Okay, the two half cycles look the same, obviously. So what I'm going to do, roll the scope, and I'm going to speed it up. So there you can see we're at half speed, more or less. So you can see the, let me go a little bit further with it. So there you can see we're almost at, that would be 90 degrees of conduction, because each half cycle is 180 degrees. So there we're just about halfway through, so that's 90 degrees of conduction. So let's phase it all the way to 0 degrees and see what happens. Roll the scope. I've taken the belt off this thing to, for one, make it quieter. Well, for one, make it safer, and secondly, make it quieter. So there we were at full conduction. So there you can see we start conducting a few degrees in, and then that conduction takes place pretty much for the full cycle. So that's full speed on the motor that we got over there, like so. Both half cycles once again look the same. So that's what phase control looks like, and what the current flowing through the motor looks like, and we're able to measure it with our CT. So that's 50 amps in the wires at 0.05 amps in the secondary. And to make this safe, take it out. There we go. So that's 1,000. If you divide that 0.05 into 50, you get 1,000. So you shift the decimal point, so it's 10, 100. 100 times 50 is 1,000. No. Yeah. Let's do the calculation. 50 divide 0.05 equals, yeah, that's 1,000. The calculator says I wasn't lying to you. I try not to. Okay, so that's 1,000 to 1. The burden resistor is 1,000 ohms. So therefore, for 1 millivolt, 1 milliamp, we get 1 millivolt. At 1,000 milliamps, we going to have 1 volt. and so on. If we were to go to 50 amps, we'd have 5 volts at 5 amps. You'd obviously need a different burden resistor, because V squared over R, yeah, you're going to have about 5 watts coming off your resistor, so you're going to need a bigger resistor at higher currents. But we know that we're not getting to dangerous power levels on a 1/4 watt resistor with this type of current that this machine draws. If you draw 50 amps through this motor, it's history anyway. It's having a bad day. So let's look at what the current was. So it's 500 millivolts per division. So we got 1, 2, and then about 0.7. So that would be half an amp, 1 amp plus 0.7, 1.7 amps. And this thing at full load is rated at 400 watts. So 220 times 1.7, we're close to 400 watts unloaded. So the maths computes. Okay, you can work these things out. It's simple arithmetic. You just got to patiently do the calculations, and you'll arrive at your numbers and results. So that was phase control on a power tool, what the current waveform looks like. But it's also an excellent demonstration of how lamp dimmers, phase controllers for heaters, and other things work, showing how the conduction works in the half cycle, and by conducting sooner in the half cycle you introduce more power to your load. That's what it's about. Okay, that's what phase control is all about. It's done in single phase and in 3-phase. 3-phase for heater control. It's also used in soft starters, where controlling the voltage to a motor during starting reduces the motor current. It also reduces the shaft torque, which is easier on transmissions. That's what a soft starter does. And it can do one other thing. You can do that for stopping as well. It's called soft stopping. It's so that you stop a water pump gradually, therefore reducing the water flow gradually, because the water has mass and therefore wants to keep moving if you suddenly stop the pump. And you get what's called water hammer, and that breaks things. So if you gradually bring the mass of water to a standstill, you don't get water hammer. So that's why we employ soft stopping on pumps, and we're controlling them on soft starters. That's one of the other benefits of being able to soft start a pump, is you can soft stop it, and that issue solved. That's also a part of my work. We work with that sort of stuff. The one thing a soft starter does not do is vary the speed for you. It's fixed speed. It ramps the voltage up, or phases the voltage up to full voltage, then the motor runs as though it's DOL. In fact, soft starters have what's called a bypass contactor in them, and that short circuits the thyristors once you're at full voltage, so you don't have current flowing through the voltages through the thyristors during normal operation, or operation between starting and stopping, constant speed. The thyristors are out of circuit because the contactor connects across it, so no current flows through the thyristors, and you don't have the voltage drop and the heating losses and the increased inefficiency of having thyristors in circuit with a bypass contactor. It's not strictly necessary, and you can do without it. It increases cost having bypass contactors, but is beneficial in other terms not having the bypass, not having them. Well, it's cheaper to not have them, but with them you have benefits of your thyrosis being out of circuit, and you're not burning off 2 volts per device per amp. So it's 2 watts for every amp that you're drawing that you're burning off as waste energy if you don't have a bypass contactor. So that's the other thing, is if you don't have a bypass contactor and your soft start is built into an enclosure, it means you have to ventilate it to get that energy out, the heat out, which means fans and filters. So generally soft starters have bypass contactors. So anyhow, we went a little bit off track with the subject of phase control, but they're related subjects. Very interesting stuff. And I think that's about all we have to talk about here. I demonstrated it nicely. This was a nice demonstration. You got to see it. If you were to look at the voltage across the motor, it would have looked kind of similar to the current waveform, except that during the current cycle, part of the cycle where no current flows, you see some voltage. It's not particularly visible on this motor because it's a wound stator motor, therefore there's no permanent magnets, so therefore there's only back EMF present while the current is flowing. Basically when the triac in this case hasn't started conducting yet, there's no current flowing in either winding, the rotor or the stator, so therefore there's no back EMF. So your waveform across your armature looks very similar to your current waveform in this case. It's different with the DC motor with permanent magnets, because there you have the rotor generating voltage whilst there's no current flowing through it. So there you have a waveform which looks kind of like a step. You have the region of no current flow with your generation, and then there's a step where the voltage goes higher when current flows, and then you see it come down again as the mains waveform comes down. Then it goes back to the region where it's generating. So it's kind of like a step with a bit of a sawtooth on the end. That's what the the voltage looks like with permanent magnet motors. So this is a series motor or a universal motor. So the stator and rotor or armature, I should refer to it as an armature. I'm going to get done for that. Oh dear. Stator and armature are in series. So this motor can run off DC and AC. Okay. I can prove that to you. Oh, why don't we do that? We are unplugged. You know what, this is what makes these videos interesting. You think about things while you're talking, and then say, hang on, we should have that in the video. We need to talk about this. We need to discuss. Also need to try and get this crocodile clip through the CT, like so. I'm going to use a power supply. Let's reconnect our television set over here. That was our nickname for them. In our first job we referred to them as black and white television sets. And of course they don't display pictures. They can, but they don't. It was a nickname. It was just a fun thing we used to do. So, this thing's probably not going to work, because, yeah. Oh, there we go. The triac. That's very interesting. Let's turn the CT up. Now there you can actually see the brush activity, like so. I'll tell you what's just happened. Once the noise has gone away, and I've turned the voltage down, made it safe, because at 60 volts DC it'll bite. What happened there is that the diac in the phase controller, which does the phase control for the voltage control to the motor, that diac went into conduction because we got to the 30 or 40 volts or so that it takes for diode to go into conduction, and the diode triggered the triac, and the triac, once it's in conduction, will stay in conduction, and I can prove that. So I'm going to hold the trigger in. What did I just do wrong? Okay, it started. I'm sorry if this motor is causing vibration on the microphone. I hope it's not. See how the motor is continuing to run. Let's turn this voltage up here. So there we got 10 volts per division. So 10, 20, 26, yeah, that's what our power supply says. If I go to meter, I'll be able to see the voltage there. So that's 60 volts. So you can see that as I turn the voltage down, the motor is not stopping. Because what is happening is the triac is staying in conduction, because that's how they work. It's still in conduction because there's current flowing through it. It's latched. The motor is still turning, even down to 18 volts, and there it stopped conducting now. So let's see where it stops. I'm watching the pulley at about 15 volts. Now what is probably happening is there's as the brushes commutate, and let me start it up again. Oh boy. So there's our voltage. That's 50 volts per division, so that's 60 volts. As the brushes commutate, you actually get regions where there's zero current flow, and at low voltage that's enough for the current to become small enough for the triac to go out of conduction, and then the thing stops, which we found was about 15 volts. So that's what's going on here. That was very interesting, fascinating. So indeed it didn't run off DC. Once we got high enough on the voltage to put the diac into conduction, it triggered the triac, and then the power tool kept running. And as you can see, it runs off DC just fine, because it's a universal motor. The armature and stator are in series, which means that regardless of current flow, the magnetic paths remain the same regardless of the direction of current flow. So the two magnetic fields do not reverse with respect to one another, which would cause a reverse of direction, which happens with a permanent magnet motor. In this case, both magnetic fields are changing direction on the AC cycle, therefore the motor keeps spinning in the same direction. That's how universal motor works. They're very useful. They've been around for a long time. They've been the mainstay of so many appliances where you need a compact source of rotational power in a tool or an appliance or something, and they're either continuously rated or not continuously rated, like the little hand blenders. They're not continuously rated, but it's fine for that little short period, couple of seconds, which means that you don't need a huge motor in the appliance, which makes it lighter and less bulky and less costly. Yeah, and for the amount of power that they produce, they are smaller than induction motors and lighter. So we will see them around for a very long time still. They're simple and they're brilliant pieces of engineering. And today you got to see some interesting things happening with a brush motor, and we learned some more stuff about them. I don't think anybody of you has ever seen that done here. No, I don't think so, because I haven't. Okay. Right, ladies and gentlemen, I love this one. Thanks for being here. Take care. Have a good day. I'll see you back for more interesting stuff next time. Cheers.